Alright, let's get going. I'm just going to sit down because I'm going to jump in and into my need to see code and stuff, so I'm not just being lazy, I promise. So, thanks for coming along to hear about new features inside Akka 2.6. My name is Chris Batey. I work on the core Akka team at Lightbend, so this is some of the stuff me and my team have been working on for the last year or two, I guess. Who's using Akka? Anyone using Akka in production here? Has anyone started like a process of upgrading to 2.6, or is one person? Two people. There we go. Hopefully I'll inspire you to encourage you to upgrade. We've got quite a few new features in there. Right. So I'm going to try and cover in 30 minutes, maybe 5 minutes each, mutual exclusion, event sourcing, work distribution, state distribution, co-locating Kafka partitions with Akka cluster shards, and then exposing it all via gRPC. I'm not expecting everyone to understand everything I go through because I'm going to go through them quite quickly. It's mainly to inspire you to have a look at the feature if you think it might be useful for your future applications. I'm going to go through some code rather than have code inside. It's on GitHub. You can go and grab it there. Most of the code samples in there are actually from larger Akka samples, which I'll link to. So there's an Akka samples repository where there's like more fully fleshed out versions of everything I'm going to work on, show you today. Tonight. So we're going to start off with the simplest thing, mutual exclusion. So this is typically done with semaphores, locks, monitors, etc. But when you're using Akka, you're typically using an actor to do that. In Akka 2.6, we have a new way of defining actors, which were experimental in 2.5. They were previously called Akka typed actors. We now call them actors, and we call the other one classic actors, just for terminology. So, just to remind everyone what an actor is, it is two things. It is some state, some data structures, some maps, some sets, some lists, your custom data types, as well as the code which executes on that. This is the behavior which executes on it. And you don't get to execute that behavior directly, you don't get to invoke a method which goes into your actor. You send in a message, and that allows us, the Akka runtime, to make sure that only one behavior, only one bit of code is executing on your state at any given time, which has the benefit that you don't need to worry about data races and all those scary things and data visibility. So let's have a look at what actors look like in Akka 2.6. Has anyone looked at Akka types? Okay, a few, so it's mainly new people. Who has never seen a classic actor, so like a normal Akka actor, def receive? Okay, so it's a few. So I'm going to show you now what they look like inside 2.6. So is that big enough? Can people at the back see? Good? Brilliant. Okay, so the first thing we do now when we define an actor, unlike Akka 2.5 and classic actors, as I'm going to try and keep calling them now, is you define the message type that you can send to the actor. So you can't just send any, well you can type your actor to any if you want to, from any other ones. But typically what you're going to do is define a sealed trait in a few different classes. And the example I'm going to use throughout the talk is a bank account. So we're going to build a challenger bank. We're going to take Monzo on and all of the big banks. We're only going to offer 3 bits of functionality to our customers, withdraw, deposit, and get balance. So the next difference when we get to typed actors, or Akka 2.6, is when we send a message to an actor and we want a response, we have to put an actor reference for that response in the incoming message. So if you see here in the withdrawal message, I've got an actor reference inside it, which is typed to a withdrawal response, because I want to know whether I was allowed to make that withdrawal. Did I have a sufficient balance? So I'm either going to get an acknowledgement back, which is this type just below on line 15, or I'm going to get back an insufficient funds. So that's the first big difference. So those are the messages. How do we define the state? So there's many ways you can do this, but one of the simplest ways is just to keep your state inside a method parameter. So here, the only state that we've got initially, we're going to make it a bit more complicated in a bit, is to have a balance. And that is just a long, and we're going to start off with 0. So the last thing to define is the behavior. So in Akka 2.6, we do that by using a set of methods on this behaviors factory. And the simplest one we can use, and we're going to see other ones, is receive message. And that is a function which goes from the message type of the actor. So in this case, it's our command, so the account command. And the function goes from that to the behavior that we'll use to process the next message. So we've got a nice simple one, which is deposit. And we send back an acknowledgement. We just pattern match on it. We send back the acknowledgement. and then we return a new behavior. So we're calling apply again, and we're adding the balance to the amount. For the withdrawal account, from withdrawing though, we're not necessarily going to allow someone to take money out of the account if they don't have enough. So we're first going to check, does the balance, do they have sufficient money in their account? If so, then we do the acknowledgement, we create a new behavior, which is the same, except we've negated the amount that they've withdrawn. But if they don't have enough, then we send back an insufficient funds, and we return behaviors.same, which is a special behavior to tell the Akka runtime to say, you know, whatever I processed the previous message, I just want to use that one again. And you can combine many different behaviors together. They don't all need to be one defined function like this, and you can put them in classes and all over the place. So that is what an actor looks like in 2.6, so it's a bit different to 2.5. Has anyone heard of event sourcing? Put your hands up. Yeah, I hope so. So most people are listening. Okay, so I don't need to explain what event sourcing is, because in Akka 2.6 we have completely changed the way we do event sourcing, but it's completely compatible at the data level. So you can migrate from the type of Akka that was shown in the previous talk, but we've become much more opinionated about how to do event sourcing with Akka, and it's been heavily inspired by the Lagon library framework. So we know what event sourcing is. We don't store the globally mutable state in our database, the balance, we store the events. And then Akka will handle replaying those events if you were to restart your Akka or move it from one node to the other. But we've had a good overview of that. One extra bit that I'm going to touch on though is that if you think of event sourcing as taking your current state and combining it with a new event to produce a new state, the extra bit is the fact that normally you're actually taking in external commands. So via some HTTP or gRPC interface, you're taking in messages from untrusted, scary users, and then you need to execute some logic to decide whether you want to actually persist some events. So we actually, as I said, we don't want bad events. So normally there's an extra step at the start with event sourcing, which is converting your commands into 0 if it's just a query, or turn many events depending on your use case. So let's see what event sourcing looks like in Akka 2.6. So we're going to throw this account away because our customers got particularly annoyed when every time we restart your application, we got rid of all of the balance. And we're going to start with a event source actor. That's too small. Right, so we're going to start off pretty much the same. So the commands are pretty much going to be the same messages. I've forgotten to implement the insufficient funds, so it looks like you can withdraw as much money as you want in the event source one, but that's fine. So these messages are the same. For a get balance, we respond with a long. If we get a withdrawal or a deposit, then we respond to say that's done this time, so it's slightly different. The extra thing that we've defined, which is here, is the events. So these are the actual things which are going to go in the database. These will be serialized with Protobuf or Jackson or whatever your favorite serialization library is. The state I promoted from being just a method parameter to being an actual class. So we can have a look at that. So it still just has a balance though, and then I've added a method on which represents this piece of business logic where I say I've got the current state and I apply the event and I get a new state. And I just pattern match on the event there. So if I get a withdrawal, I take it off the balance. If I get it deposited, then I add it to the balance. And so just to note the distinction here is your commands are typically specific to the fact you're using Akka, right? You've got actor refs in them, etc. Whereas your events and your states, these should be void of anything to do with the library or framework you're using. So this is just your pure business logic. We don't really have much business logic in this example, but the Akka doesn't need to know, you don't need to know anything about Akka for doing your events and your state. So the next thing we need to do is define how to map our commands into whether we want to persist them events. Do we want to do something that the user has asked us to do? So in Akka persistence types, that is called the command handler. And rather than being a function from command to the next behavior, it is a slightly fancier function, and it takes the current state, it takes the commands, and then you have to return an effect. An effect is how you're going to tell the Akka runtime whether you want to persist some events, or send a reply, or do nothing, or whatever you like. So let's see what that looks like. So we pattern match on the command, and we do some logging, and then if we want to persist events, so these things are going to be permanent. If we persist events, when we restart, these things will be replayed to us. We just call effect.persist, and we pass in the deposited event. And then we can also chain on lots of things. So one example is we can chain a side effect onto here. So once the event has made it into the database, so we know it's in the database, then we can execute like side effects which say, okay, respond to the user. And once that side effect has been called, once those things are executed, we know, unless we have our DBAs have an extremely bad day, that when we restart, those events will be persistent, they'll be durable. But we might want to do nothing. So in this example, we've got a query-only command. So we're not going to record anything in the database to say someone queried the balance. Users can do that as much as they want. We just respond, and then we return effect.null. The last thing that we need to do is turn this into behavior, because that is what you can start. That's what you can give to an actor system or an actor to say, hey, spawn this. So we need to turn it into a behavior. So the last step is to put all this together, create one of these event source behaviors, and we pass in a few extra things. So the first thing is a persistence ID. This is a unique identifier. It's what segregates the events for a particular account in this example in the database. Of course, we don't want to build a system where you can have one bank account, so we want to have lots of bank accounts for all of our users. We've got an empty state. So this is the state which is passed into the command handler when you don't have any events yet. So this is your first one. And we're just going to do a balance of 0. Finally, we pass in that command handler, so I just defined it as a separate method at the top just to make things easier. And then the event handler. So the event handler is the thing which is executed once the event has been persisted in the database, and all we do is delegate to our business logic. So Akka doesn't really care what you do as long as you create a new state from the existing event. And once you've got one of these behaviors, if we look down, actually we see what that typed to. It's an event source behavior, and there's like lots of extra functions, like there's lots of extra builder things that I can add onto here, like I can have automatic snapshotting and pick a snapshot plugin, which is where you pick, say, between JVC or Cassandra or Couchbase, etc. But this types down to a behavior.command, so I can spawn that, like I can start an actor like after all, but now it's called spawn. So that is event sourcing in Akka 2.6. The biggest changes are the fact that Akka now knows about the types, it knows the type of your commands, it knows the type of your events, and it knows the type of your state. So we can do things like automatic snapshotting and be smarter about knowing which event adapters which would be valid for this particular behavior. Next, work distribution. So we've added 2 extra features into Akka 2.6. which pull out some patterns which we've seen repeatedly prior to 2.6. So this is a problem that comes up quite a bit that people want to solve. They've got a big computation to do, or they've got an infinite list of work, or they take work in, but they want to spread it across many machines. And this is a problem that starts off, you think, well, I can solve this, I'm just going to write some code, it'll be quite easy. I'm going to have my node start up in Amazon, and they're going to register with something, and then I'm going to send work, and I'm going to get acknowledgements, but it very quickly becomes very complicated, and we've got a sample in the Akka samples repository, which I'll link, which shows how to do this effectively in 2.5. And it handles things like the workers crashing. It handles message loss between like the thing which is just managing the work and the workers. It handles redelivery. It handles message item potency by adding sequence numbers. And this thing becomes very complicated very quickly. So we've added 2 features to Akka 2.6 to make building rough patterns like this much easier. So the first is the cluster receptionist. So the cluster receptionist is basically service discovery for typed actors. So you can register yourself and you give yourself a name, and it's an extra bit of information which encodes the type of message that you can receive. And then other nodes running in a set of Akka nodes can listen to that and subscribe and be told when new ones are added. But you also get told, oh, has this node crashed? Has this node left the cluster of Akka nodes? So it handles all of those cases for you. The other bit of functionality, which is a bit more complicated, is reliable delivery. So all of that stuff around messages being idempotent, redeliveries, retries, is encoded in the blue bit in the middle, which is relatively complicated if you implement yourself. The green bits, so the producer and the consumer, they're the bits that you do. So as a producer, really all I want to do is to know when I'm allowed to send a message. I could just send a message, that could be fine, but I might overload or it might get dropped in network buffers, etc. So the way reliable delivery works in Akka 2.6 is you're actually explicitly told, you can send the message now and you get this request next message, and then you can send it. On the other side, a consumer of some work or some message, you can be told that here's a delivery, here's a message, it comes from the other side. And it's then your responsibility to confirm it. Now, you could confirm it right away, you could confirm it an hour later, you could do some big CPU-bound computation, you could do an asynchronous computation, but basically, you do the confirmation, and then Akka handles everything in the middle. So what type of things does it do? Well, the first thing it does is it sequence numbers your messages. So that means that it can retry, and then we can do deduplication on the other side. It does windowing of requests, so it's got flow control built into it. So if you were to do this by yourself, and you were to do, say, an ask from the producer to the consumer, you're doing like one request, one response, one request, one response, which is a really easy programming model, but it's not very efficient. Really, you want to send bulks of messages over the network, and you want to, and if the consumer suddenly has processed 10, you want to send back, oh, all 10 are done with one small message. You don't want to send back 10 acknowledgements, ideally. So that's the stuff that it handles under the covers. And this composes into something bigger. It can fan out messages. So you can have a producer which registers itself with across the receptionist, and then you have lots and lots of consumers that can dynamically register. But the programming API that you use on the producer side is just the same. It's like, give me a message. Okay, here you go. Give me a message. Here you go. And on the worker side, on the consumer side, you just process one message, acknowledge one message, or you can process multiple messages and then acknowledge a bunch of them. And then Akka will handle the workers registering and doing redelivery and load balancing across all the nodes that have registered with the receptionist. And in the Akka samples repository, we've got this as in 2.5, and then there's a PR open right now which converts it to using this feature. And it basically just deletes 80 to 90% of the code. In 30 minutes, I don't have time to show you that one, so I'm just going to skip by, but there's an extensive sample for how to use reliable delivery. Next feature, state distribution. So I'm going to talk about how to distribute our event source actors across many nodes. I'm going to talk about a feature which is not new, but we've made it a lot easier to use in Akka 2.6. So, as a very popular challenger bank, we started off on one node running in Amazon, and we were doing fantastically well. And we were event sourcing, so we've got things in memory, which means that we're extremely responsive for the queries, because we don't need to go into our database. But everything kind of becomes problematic once we scale to multiple nodes. How do we decide which actors to start on which node? Do we stop them every single time and then restart and replay the state, or do we keep them in memory? And we typically try to build stateless applications these days because it's much easier to deploy stateless applications to environments like Kubernetes. And by stateless applications, I mean we just hide all our state in the database and we rely on transactions and locks and hitting the database for every single thing. Even if it's two parts of our application trying to communicate, we'll just go via the database because the requests could have come into different nodes. But the advantage is it means that load balancing in front of our application can be very dumb, which means that our application is easy to deploy in lots of different environments. We don't want to have to route all requests for a particular account or a particular user to one node, right? Because that means that we need smart and clever things in our load balancer, and bad things happen when that node crashes. All of the stuff in the memory goes away, etc. So we've had a feature called Akka cluster sharding in Akka for quite some time. And this is a way of having entities, actors, be them event sourced or not. You give responsibility to the Akka runtime to start them for you and route messages to them. So rather than call actor or spawn and then start sending messages, you go via sharding. And then the Akka runtime will decide where to run that actor for you. And it might be local on your node, or it might be on a completely different node, and it will happen transparently. Which means that we can have the advantages of things being in memory and things being super quick and being able to make decisions very quickly, but then we don't need our load balancer to get involved. The request can come into any Akka node and it will get transparently routed. And we've made this quite a bit easier to use in Akka 2.6, I hope, or we should try. So we're going to stick with the same event source entity. We don't need to change the actor itself to become part of sharding. We just need to interact with it differently. We don't get to just start it ourselves and send messages to it. We get to tell sharding how to start it. So let's have a look what that looks like. So if you've used sharding before in Akka 2.5, then it was to an untyped actor, so you can send whatever you want, but that's not what we want in Akka 2.6. We want to only be able to send messages of the right type to it. So we create this entity type key, and we have the type of the message. So this account.command is what we defined, what we looked at in the event sourcing section. And then we give it a name, and that's just to uniquely identify it. We could have two sets of sharded actors for the same type but different names if we wanted. It's not too common. And then, to get an actor reference to actually send messages to it, we have to go via sharding. So what do? So we create this thing called an entity, we pass in the type key, and then a function which is going to create the initial behavior for it. And here I'm just calling the account apply method, and that is what we saw in the previous section. So we can see it's just this account that we defined before. And then to get the actor reference to actually send messages to it, a sharding-based actor reference, we call cluster_sharding.init, we pass the entity, and then we get back this. It's the actor reference of sharding envelope of the type of message that the actor is allowed to receive. So we can't just send messages to it directly, because which account would it go to, which actor would it go to? So we actually have to go to this sharding envelope, which is a really simple case pass, right at the bottom here, which includes the entity ID, and that includes which account we're going to send the message to, and then the message itself, which is just your user message. And to use this, let's have a look at a little main method. We call our initialization that I just showed you. So we get back an after reference, which we send sharded envelopes to, and then we just start sending messages to it. So from like a HTTP endpoint or a gRPC endpoint, you can send these messages with the sharding envelope, and it would get routed to wherever that actor was running. If it wasn't running, it would be started. If it needs to be moved, messages will be buffered in memory and then sent once it's been moved to another node. So you're scaling, you're adding nodes to your application. Next, distributed data processing. So our Challenger Bank, we're very successful. We've offered our 3 features of withdraw, deposit, and get balance, but we now want to start doing some analytics, so we can give you a yearly summary of how many times you've been to McDonald's. And for that, we're going to stick all the messages on Kafka, and we're going to process them with a cluster of Akka nodes. So Kafka, the 30-second overview of Kafka is it is a message queue, a message broker, a message topic, which can be partitioned, which means it can be spread on multiple nodes. And then you can consume those partitions, and you can consume them with 1, 2, 10, as many nodes as you like. And what Kafka will do for you inside a consumer group is allocate partitions to the nodes which are registered in that consumer group. So if we make sure that all of our information about what our users are up to end up in Kafka, and we make sure that all messages for the same entity, so in our case that's the account ID, but in your case it might be device or user, etc., end up in the same partition, then on each Akka node, we can consume that and make sure that all messages for the same account end up on the same node. And if you had entirely stateless processing, by stateless I mean one message is in no way related to any other message, you would not need any fancy Akka features. You would just use whatever Kafka consuming library that you chose, and the Kafka consumer group would handle it all for you. Because Kafka already handles things like if we were to add more nodes, it would rebalance the consumption of the partitions across more nodes or fewer nodes. But not many analytics use cases are stateless. There's not many interesting things you can do. Sometimes we take the same approach, we just start interacting with the database a lot. So we can combine this type of consumption from Kafka with Akka cluster sharding to create stateless, so stateful processing. So rather than process the message locally, we're going to send it via sharding to a sharded actor, which is then going to do the processing. Which means in memory we can keep the current state. We can keep, say, the current balance, and we can see whether they're doing a particular account has suspicious transactions, and we can keep that in memory. And that works fine, and that actually works fine in 2.5. The only thing that's changed is that we now interact with sharding via the type markup and make use of the type system rather than send anything. The new feature that we just dropped in Akka 2.6.2 is being able to have much more control about where Akka puts the actors. So a really common thing that has been requested quite a lot is if I'm going to process, if the Kafka consumer group has decided to consume partition 0 on this node here at the top, well, I would much rather my actors for account 1 and account 2, say my account and someone else's account, to be co-located with it. And if the Kafka consumer group were to say move it over to this node here, I'd really like all of the Akka nodes to move with it. So that means that we don't end up with an extra message hop for each of our messages, and that's the feature we just added. So I can show you roughly what that looks like. Just to really process it big enough. Right. So we've got another type. This is the serialized. This is the type which is representing the message on the Kafka topic. So I assume we've got some different data representation on the Kafka. We're going to start an Akka system, and an Akka system now has a root behavior, which is where you can, well, it always did, but now you have to provide one, which can do your initialization. So inside that behavior, I'm going to connect to Kafka, I'm going to initialize sharding, I'm going to then set it up so all messages from my Kafka topic are going to end up being sent to sharding. So let's see what that looks like. So I'm going to use a library called Alpaca Kafka. It is just an Akka streams-based interface for consuming from Kafka. I'm not going to go into really what that does today. But we've got some settings, like talk to Bootstrap servers, etc. But we're going to subscribe to a single topic. And then we've got this thing. This is Alpaca Kafka, this consumer. And we can say we just want a plain source, which basically says, give me the messages as a byte array, and I'll do what I want with them. I parse them, I use Jackson because I was lazy and it was just already on the class path, and I get back my account withdrawn or my account deposit message. And then what I do is I do an ask, which is a request response to an actor, rather than just an asynchronous send. But I don't send it to an actor which I've created, I send it to accounts. What is accounts? Well, accounts is the sharded actor that we initialize. So this type here is an actor reference of sharding envelope of the account command. So basically I send it off to my sharded actor, and that means that sharded actor can keep some memory about that distributed processing in memory and then keep updating it every time the user does something. So the last feature, oh by the way, to make it co-locate with Kafka partitions, it's just some extra configuration, and we've got an extensive sample for that inside Akka samples, so you can, with instructions on how to run it and to kill Akka nodes and see everything moving. So the final one is gRPC. So we've built this application, but we haven't talked about how we're going to interface. What's the ingress going to be? How are we going to get in there? So, and one of the big advantages of doing things like these analytics jobs inside with Akka cluster sharding is that the messages from the Kafka topic can get sent to the sharded actor. But in real time, we can also send queries. So we can have messages come in over HTTP or gRPC or however they might come in, and we can, in real time, see the state of that analytical job. We don't need to save it to a database and then get it from there, etc. We can go directly in. And that's because we can go via that, sharding envelope actor reference and, make a query to it. So let's see what that will look like. So, gRPC. So gRPC is a language agnostic way to do remote procedure calls. It's an alternative to, say, doing JSON over HTTP. We released Akka gRPC 6 months ago, maybe a year ago, maybe 6 months ago. And it's a way of basically using an Akka streams-based interface for interacting with gRPC. So here's a really simple service. It's in an IDL that's specific to gRPC and protobuf. We're going to say we've got one method, it's called the get account balance, which is going to get the current balance because that's going to be processed in our analytical framework. It just takes in one message and it returns another one. gRPC supports streaming as a first-class citizen. So you can, and if you were, I'm not using streaming in this example, but if you were to use streaming, you'd end up with Akka stream sources rather than what I'm about to show you. So we've got an SBT plugin that generates you a traits to interface, so let's have a look at that. So this is generated code. This is from that IDL, this is the Scala trait which you have to implement to expose that gRPC service. So it generates you some case classes, like get account balance request and then a response. We assume everything, you want to do everything asynchronously, so for normal like request response things, you get a future. For anything streamy, you get like a stream source. So then we want to have a look at the implementation. So the implementation is going to be quite simple. We're going to pass in, when we construct it, that Akka reference, that way of interacting with sharding. So it means that a gRPC request can come into any node in the any Akka node, and as long as it sends its requests via sharding, it's going to end up at the right place. So let's see how we implement that method. Well, we go to the sharded Akka, we do an ask, which is a request response. We get the balance back, and then we respond. And we don't need, the load balancer doesn't need to know which node to go to. The actual actor that we're talking to will get moved around when the Kafka consumer group moves things around, and all that will happen transparently under the code. How do you start that? So this is the same example I was just showing with the Kafka consumption. We can also start gRPC as well inside the same application. So, another generated class, this account services handler. You pass in your implementation, and you get back something which types to a HTTP request, the future of HTTP response. So gRPC itself runs over HTTP, over HTTP2. So the Akka gRPC just generates you this utility which can give you a function from HTTP request, the future of HTTP response. And then you can plumb that into regular old Akka HTTP, because that type is agnostic of anything to do with gRPC. And I think this might be unique on the JVM. This means you can actually combine your normal HTTP endpoints with gRPC endpoints on the same port. Because Akka HTTP, you can compose those things, and then you can just give Akka HTTP some normal routes, some normal HTTP, JSON-y stuff, and gRPC. Right, that was a lot. Hopefully you got some of it. That was actors, event sourcing, the work distribution with the receptionist and the reliable delivery, state distribution, gRPC, and co-locating Kafka consumption of Kafka partitions with the actors which are going to do the actual processing. So thanks very much for listening, and I'll be around for questions if you want for after.